Okay, so we've covered two types of linear optimization problems. We've made Excel models to represent them and then used Analytic Solver platform to solve them. They were simple models that were either trying to, in one case, maximize profit, maximize the objective subject to maximum constraints, that is, capacities that you can't over-allocate things. And then the recent example was a coverage model, which tries to minimize something. The objective was cost. We're minimizing cost subject to minimums, so minimum nutrition in that case. So those are some straightforward models. We're going to talk about another kind of model, but we're going to go back to a previous example for it. So we're actually going to go back to the furniture making example and say we're going to add a new type of constraint. Okay, so let's assume in this case that we wanted to make a minimum number of chairs, but the minimum number is not just a flat number. That is, we don't want to say you have to make 10 chairs. What we want to say is, of all the product we make, chairs, desks, and tables, we want 10% of it to be chairs. Okay, so the number of chairs we make is dependent on the number of desks and tables we make. Okay, but there's a minimum amount. Okay, so we're going to add in a new kind of constraint. Now, to represent that constraint, I'm actually going to go to the whiteboard behind me and represent how you can compute that constraint. Okay, so let's say if we had our decision variables was the number of chairs, the number of desks, and the number of tables. Okay, and we wanted to add a new constraint that says, well, the number of chairs you make divided by chairs plus desks plus tables. So that's the proportion of chairs out of all products that you make. We want to set that to be greater than or equal to 10% or 0.1. Okay. So that's a new kind of constraint that we want to have. But there's a problem with this constraint. It's not linear. That is, it's not numbers multiplied by our decision variables added up. Right? It involves one decision variable divided by others. Okay? So it's not a linear constraint the way it's written here. So what we need to do is we need to transform this algebraically into a linear constraint. So if we multiplied both sides of this inequality by the denominator here, okay, it would transform this into C must be greater than or equal to 0.1 C plus 0.1 D plus 0.1 T, right? Okay. I want to make sure everybody followed me. We took this constraint, the proportion of chairs to all things must be greater than or equal to 0.1. That is, we have to make at least 10% of our products as chairs. We transform that into a different looking constraint that says C, 1C, must be greater than or equal to 0.1C plus 0.1D plus 0.1T. Okay? So we're going to modify this a little more so that we have all our decision variables on one side of the inequality. Okay? So we could rewrite this as 0.9C minus 0.1D minus 0.1T. Oops. Got ahead of myself. 0.1T must be greater than or equal to 0. Okay? So we just took a constraint on proportion of chairs to all other things being constrained and turned that into this sort of less intuitive form, right? That says 0.9 chairs, number of chairs, minus 0.1 number of desks, minus 0.1 number of tables must be greater than or equal to 0. But this equation here is the same thing as that one, just in a different form. Okay? So we've taken this proportionality constraint and just turned it into what looks like a normal constraint, linear constraint. Some number times each decision variable added up, or in this case, some added, some subtracted. That's fine. And that's constrained to be greater than or equal to 0 in this case, some value. Okay? So we're going to take that constraint in this form, put it in Excel as really constraining the proportion of chairs. So all we're saying is we don't want to make less than 10% of all the things we make as chairs. Okay? So we have to make at least 10% of everything as a chair. So this is going to be our chairs 10% constraint. Okay, I'm just going to name it that. And again, what we figured out is if we multiply 0.9 times the number of chairs and add to that negative 0.1 times the number of desks and add to that negative 0.1 number of tables. Okay, so that's our sum product coefficients, right? So 0.9 chairs minus 0.1 desks minus 0.1 tables added up. That's going to be constrained to be greater than or equal to 0. Okay? So obviously right now that constraint's violated, right? We have negative can't be greater than or equal to 0, which is obvious because we're not making any chairs, right? So we need to make at least some chairs. Let's say we made, 50 chairs. Well, that certainly satisfies the 10% chairs constraint, but now we are probably over on some of our other constraints. Okay, so let's add that constraint into the model. So we've added it in the spreadsheet, but we have to tell the model, the Analytics Solver platform model, about this constraint. So I have this value computed here, and E16 is going to be constrained to be greater than or equal to the value in G16, okay, 0. So now that I've added that constraint to the model, I can recompute or re-optimize, and it's found a new optimum solution. Okay. In this case, to get us a profit of $8,361 by making 38.79 chairs and 249.13 tables, or desks, and 100 tables. Okay, so we've definitely met that constraint. You'll see that the chair percentage is a binding constraint, as you would have expected, because we prefer to make less 0 chairs for the best profit. But since we have to make at least some chairs, we found out it's better to make 38 point something of them and make the rest of what we can in desks and tables to optimize or maximize profit. Okay. Now we're going to come back later, probably next week, and talk about how you could further constrain this to say all these decisions must be whole numbers. Okay. Obviously, it doesn't make sense to make 38.79 chairs. However, in the real world, that wouldn't be so much of a problem, because in the real world, you could look at this and just round and say, well, let's just make 39 chairs and 249 desks, and that'll be very close to the optimal solution. Okay. Or if you were worried about fabrication hours and such, you could just round every value down, right, and still stay under your constraints, but pretty close, right? You would be at almost the best profit possible, subject to obviously making a whole chair rather than half a chair or something. Okay, but we'll come back and talk about if you had to constrain things to be whole numbers, how to do it next time. All right, so this was our new kind of constraint, and when you have a constraint like this, technically we would classify this as a blended model. So it's no longer an allocation model, because it involves this constraint that isn't just a capacity constraint. That is, you have so much capacity that you can't go over. In this case, it's actually a less than or equal to constraint, not greater than. I'm sorry, it's a greater than or equal to constraint, not less than or equal to. And it's computed, intuitively we want to compute it as the proportion of chairs, but instead we had to write it as this sort of different form of 0.9 minus 0.1 minus 0.1. Okay. Okay. Any questions about any of that?
What do the values mean?
Okay, so those 0.9, negative 0.1, negative 0.1, I'm going to come back to the board here and say, remember, this was how we represented a linear function of this constraint. So the number of chairs divided by the number of everything. So we wanted the proportion of chairs to everything we make to be greater than or equal to 10%, 0.1. So however many desks and tables we made, we wanted the number of chairs we made to be 10% of the overall products. Okay? And we just took that constraint and algebraically manipulated it to get this equation. It's easier, right, intuitively to think in this equation. In terms of putting the equation in Excel, the way we've set up Excel with sum product and all of our constraints listed in sort of rows, it's easier to rewrite it in this form. Okay. Now also, okay, just to let you know, if you computed in Excel this value, okay, and put that value as constrained to be greater than or equal to 0.1, Excel could solve that. However, it couldn't identify and couldn't know that the model is technically a linear one. So it would have to actually revert to a different form of an algorithm to solve the model. And in that case, it actually might not give you the optimal solution. Remember, I talked about how linear models will always find a solution because all it has to do is find where the constraints converge and pick the one with the best objective. Other kinds of models that aren't linear, we can solve but aren't guaranteed to get optimal solutions. Okay? So if you put this equation into Excel, it would solve and get you an answer, but not an optimal one, not necessarily. Okay? But writing it this way guarantees that it's a linear model, linear constraint, and can be solved optimally. Okay. All right, let's do another example involving the same essential thing. So in this case, we're actually going to make, similar to our trail mix example last time, we're going to make a blend of coffee beans, okay, to make some coffee grounds, okay, for making coffee. So the coffee beans we have available to us, we're going to have three different kinds. So have our decision variables. In this case, we're talking about coffee beans, and we have three different kinds. We have Brazilian coffee beans, we have Colombian coffee beans, and we have Peruvian coffee beans. Okay, so let's just say we take, I'm just going to assume 1 pound, let's say, of each to start with. So those are my decision variables. I'm going to compute an objective. In this case, our objective is going to be somewhat similar to what we had before in that we're trying to minimize costs. Okay, so similar to the coverage model, we're going to represent here the cost of each pound of these coffee beans. So let's say Brazilian beans cost $0.50 per pound, Colombian 0.6, and Peruvian 0.7. So if we take the sum product of how many pounds of beans multiplied by the cost per pound, that would get us the cost per pound of the mix of beans. Okay. So I'm just going to format those as currency numbers and then fill the cell which is our objective, which is the cost per pound of our coffee mix. Okay. And now we're going to have our constraints. And similar to how we had nutritional constraints for our trail mix, we're going to have different kinds of constraints for our coffee beans in terms of we want our coffee to have a certain aroma. So different beans have a different, we're going to say, numerical value for aroma. Some are better smelling, some are not better smelling. Let's say. So we have a aroma constraint, but we also have a strength in terms of how strong the coffee is. Okay, if you're a coffee drinker, you can appreciate that. If you're not, then it's okay. So each bean has a different aroma value to it, different amount of goodness to its smell, and each coffee bean has an amount of strength in terms of how strong it makes the coffee. Okay, so we've been given these parameters. So each Brazilian beans have an aroma content or value of 75 and so forth. So we're just going to use the standard sum product to multiply our decision variables by our constraint parameters. I'm going to remember to make the decision variable references absolute, so I can just copy the formula. And we have a minimum amount of aroma rating, which I believe is 78, and a minimum strength rating of 16. Okay. So those are our constraints so far. But we're also going to add some capacity constraints to say we have only so many pounds of each bean available. Okay, so for each pound of bean we use, right, we're going to constrain the total amount of pounds. There we go. To be, make sure I get these values. Okay. 1.5 million pounds of Brazilian beans, 1.2 million pounds of Colombian, and 2 million pounds of Peruvian beans. Okay. Now, we also have a different kind of constraint in terms of the demand. So we actually have so many pounds of coffee, regardless of its makeup, that we have to make. Okay. So we have to make at least 4 million pounds of coffee. And actually, I've written this wrong, so we can't have, these are less than or equal to constraints, because we can have more than 1.5 million, or 1.5 million pounds of Brazilian coffee beans. That's all we have available. We can't have more than 1.2 million Colombian, 2 million Peruvian beans. But we need to make a mix that together, however many pounds of beans we use per mix, together that use 4 million pounds of coffee. Okay. All right. Let's see here. I think that covers everything. All right. So let's specify the model by telling it what our decision variables are, what our objective is. In this case, we're minimizing cost per pound. Okay. And now we have to be a little bit careful because some of our constraints are greater than or equal to, some of them are going to be less than or equal to. Okay. So in this case, the aroma constraint, which, looking back now, I think I may have got that wrong. Okay, let's look right. So those constraints must be greater than or equal to the corresponding aroma strength. The capacities must be constrained to be less than or equal to the available beans, and the demand must be greater than or equal to the minimum amount of demand we have to make. So the minimum amount of pounds we need to make. So let's solve. I think I did do something wrong. However, I did get an answer. So let's look and say. So we found that we needed to use 1.5 million pounds of Brazilian beans, which was the maximum we could use. Forgot to add my binding tests. So we can easily see which constraints are binding and which are not. So we used the maximum amount of Brazilian beans we could and the maximum amount of Colombian beans we could, but not as many Peruvian beans as we could have used in order to make the minimum 4 million pounds worth for the lowest cost. Okay. Now I did do something wrong with aroma and strength. I think I've misread. Let's see how they did this. Those are blended constraints. That makes sense. So what we want to do is average these values subject to their proportion of beans and make sure the average, that the weighted average, is at least 78. So again, I'm going to step back to the board and we'll rewrite that constraint. So if we take the number of we're going to use B for Brazilian beans. So the Brazilian beans have an aroma rating of 75. We'll use C for Colombian. So 60 Colombian beans. And is that 85? 85 for the Peruvian beans. Okay, so these are the aroma ratings. Okay, but we want to divide that, right, by the total number of beans, because we want the aroma rating of a single pound of beans to be at least 75, 78. So this is another blended constraint. It involves sort of proportion, in this case, a kind of a weighted average. So Brazilian beans get weighted by 75, Colombian beans get weighted by 60, and Peruvian beans get weighted by 85. But the normalized number for the total number of beans, right, needs to be 78. Okay? So we need to rewrite this constraint in terms of an inequality with a linear function. Okay? So we can rewrite this as 75b, 60c, 85p is greater than or equal to, we can just multiply the b plus c plus p over to the other side and get 78 times each one. Okay? So I've rewritten the black formula as the red. Okay. And now we just need to, move all of the decision variables to one side, effectively. Okay? So we can have some function of the decision variables be greater than or equal to 0. Okay? So if we subtract 78 Brazilian beans from each side, we get negative 3 times the number of Brazilian beans. Okay? Minus 18 times the Colombian beans, plus 7 times the Peruvian beans is greater than or equal to 0. Okay, so that's our equation. So we've taken this weighted average or blend of the aromas for each bean, being a minimum of 78, rewritten that as negative 3 times the Brazilian beans, minus 18 times the Colombian beans, plus 7 times the Peruvian must be positive, greater than or equal to 0. So let's put that equation in. So I wanted negative 3, negative 18, 7. okay, times each of those. That needs to be greater than or equal to 78 times the sum of these, okay? Oh. So one, that's this. This isn't working at all. Okay. So that's one way I can compute it. Oh, I'm sorry, this needed to be 0. What am I doing? So -3 times the number of Brazilian beans minus 18 times Colombian beans plus 7 times the Peruvian beans should be positive, greater than or equal to 0. And you can do the same thing with strength. So let's quickly compute the strengths. So 15B, 20C, and 18P, okay, would need to be greater than or equal to the average 16 times B plus C plus P, okay, which means -1B plus 4C plus 2P is greater than or equal to 0. Okay. So same basic approach, skipped a step in there, simplified, and we get this equation represents, again, the weighted average of the beans. So 15 for every Brazilian bean, 20 for every Colombian bean, and 18 for every Peruvian bean needs to be at least 16. Okay. So we'll use those values. 1, 4, 2, greater than or equal to 6. Okay. All right, so now let's solve. All right, that's better. So what we found was we're going to use all the Brazilian beans we can. So that's a binding constraint. And then we're going to use some mix of Colombian and Peruvian beans, less than the maximums we could, okay, subject to obviously the aroma constraint being binding. Okay, so for every Colombian bean we used, that decreased the aroma. So we needed to use more Peruvian beans to increase the aroma back. Okay. And basically we found a mix of the minimum amount of Colombian and Peruvian beans we could choose to keep the aroma, right, positive in this case, the aroma at least being 78, but minimize the costs. So the minimum amount of beans, because we're minimizing costs, subject to being at least 4 million beans, but to keep the aroma as pleasant as possible. Now you might want to compute the actual, and so this isn't a constraint, but let's just prove that if we took 75 times the number of Brazilian beans, 60 times the number of Colombian beans, and 85 times the number Peruvian beans, and we divided that by the sum of the number of beans. So here we're just computing the weighted average, but that is in fact 78. Okay, we wanted that to be at least 78. We rewrote that equation into these coefficients and made that subject to being greater than or equal to 0. Okay. And just for fun, let's do the same for strength. So even though strength was not a binding constraint, what that should mean is our strength being a minimum of 16, we probably are far above the 16. So let's just confirm that. Yeah. So we wanted the strength to be at least 78, and the aroma to be at least 78, and the strength to be at least 16. And it was the aroma that became a binding constraint, Now again, the reason I don't use this equation down here in E19 that involves a sum product divided by a sum of the decision variables, because that's no longer a linear function. It's no longer linear in terms of the decision variables. It's one decision variable divided by another, effectively. So that's not a linear function. So I had to rewrite the constraint like this. But you can see it meant the same thing. This being 0, greater than or equal to 0, was the same as this being greater than or equal to 78. Okay, so that's another blended model, okay, where we're taking constraints, in this case of several different forms. One is capacity constraints, that is, you can't go above this amount. Another is a coverage kind of constraint, that means you have to have at least this amount of something. And then finally some blended constraints that involve proportions, weighted averages of decision variables. By and large, okay, what trips more people up than anything else are these blended constraints, right? If you can write it intuitively, okay, like we did the number of chairs divided by chairs plus desks plus tables, proportion of chairs needs to be at least 0.1, 10%, then writing that out intuitively and algebraically converting it to something that's a linear function constrained to be some value, usually 0, okay, then you can put that constraint into Excel in the standard form using the sum product function and write the constraint in a way that's linear. Okay, so practice will make perfect at that. Okay, all right. Let's do one more thing, and then we'll be done for the evening. Okay, and the last thing we're going to do is talk about sensitivity. Okay, sensitivity is testing how sensitive the optimal solution is to certain of the constraints. Okay, so we know, for example, I'm going to go back to our furniture model. Okay, so we know which constraints are binding. Okay, in this case, the fabrication department hours, the demand for tables, and the minimum percent proportion of chairs are all constraining or binding constraints. But what we might want to ask is, how could the optimal profit change by changing some of those parameters with those constraints? Okay, or even changing any other parameter. So for example, we might say, how much better of a profit could we get if we had more fabrication hours, more fabrication department hours? That is, if we could hire more people to work in the fabrication department, how much more profit would we get? Okay, so we could, for example, just put in a new number. Say instead of 1850, let's assume we were constrained only by 1900 hours, and we re-optimized. So our old profit, I'm going to use a base case or benchmarking, okay, technique here. Paste that. So we know the old fabrication hours of 1850 led to a maximum profit of $8,361. But now if we constrain fabrication hours just to be less than or equal to 1900 and resolve, we can make theoretically more profit, $8,560. Okay. Again, we're using all the hours of fabrication that we have available. So I'm just going to copy that so we can remember it. So 1900 hours gave us 8,560 profit. Well, let's say we really had as much fabrication hours as we wanted. Okay, so I'm going to put in 10,000. Okay. Should be more than enough to make as much as we want. Okay, let's say that wasn't going to be our constraint, our binding constraint anymore. Let's resolve and find out what becomes binding. So a new profit of 11,700 obviously we got more than enough fabrication hours, but now we're being constrained by our assembly and shipping department hours. So both of those have simultaneously become binding constraints. Okay, that is, we've determined now if we're going to have to make at least 10% chairs, and we can't make more than 360 chairs, 300 desks, and 100 tables, and we're trying to maximize profit, then we're going to use all the assembly and shipping department hours to make chairs and desks. As many desks as we can, and then as many chairs beyond that as possible. Okay. So you can see how just changing one parameter in the whole model obviously changes the objective. And in this case, changed quite a bit about the decisions to be made. Okay. So again, if I went back down to 1900, then the optimal decision was to make chairs, desks, and tables. But when I had more than enough fabrication hours available, we made 0 tables. So not only did we get a different objective, profit, we actually made a different optimal decision. Okay? So it would be useful if we can systematically go through and find out more information about how that pattern changes. Okay? That's what we call sensitivity analysis. Okay? How sensitive is the optimal solution in terms of what decision variables get made, or decisions get made, and what objective is computed. How sensitive is that to changes in some of these parameters? Okay? So, to do that, what we're going to do on the Analytics Solver platform toolbar, there's a button called Parameters. Okay? So I'm going to select an empty cell, in this case G9, okay? And I'm going to input into that this Parameters button, something called Optimization, okay? Which means I want to find a new optimal solution subject to changes in some parameter. Okay, so Parameters Optimization. And here you're going to put in, essentially we're just going to put in lower bound and upper bound values. In this case, we want to say, we know originally we had 1,850 fabrication hours, and let's say we know we can use up to 10,000. Well, let's make it a little easier. Let's do 4,850. Okay, something I can remember easier. So we have a range of 3,000 hours here, of fabrication hours that we want to use. Okay, so I've put that in. Now you'll see this function that it included is now PSI opt param, standing for optimization parameter. Okay, and it has our lower and upper bounds. So now what we're going to do is set the parameter here, the number of fabrication hours, equal to the cell that has that PSI opt param function in it. Okay, so G10 equals G9. G9 has that new formula in it that we got from clicking the parameters button. Okay, so all we're doing is we're setting up a case to say we're interested in how sensitive this solution is to the number of fabrication hours available. And we might have 1,850 up to 4,850 hours available. So now what we're going to do is I'm going to have it generate a report, a table, to say how does the optimal solution change for different values of this parameter, fabrication hours, okay, in this range, 1,850 to 4,850. So I'm going to click on the Analysis ribbon, the Reports button. Under that, the Optimization menu, and under that, Parameter Analysis. Okay, so leave that on screen for a second so you can see. So we're the Reports button, Optimization menu, Parameter Analysis. That will bring up a new dialog that says, here's the parameter that I know how to change, G9. That's the cell that had, if you remember, cell that had PSI opt param function in it. And I can tell it how many data points, that is, how many different values of that parameter I want it to test with in that range that I put. So I had a range of 3,000. So let's do maybe 31 different values. Okay, and I want it to generate a report that tells me, I'm going to click all these variable fields up here. So I want to know, how does B4, C4, and D4, the decision variables, how do those change when G9 changes? And I also am curious about the objective, E7. So how does our optimal profit and our decisions of how many chairs, desks, and tables to make change as the number of fabrication hours change? So it's going to rerun optimizing one time for every change in that parameter and generate a report. Okay, so I'm going to say OK. It's going to generate a new Excel spreadsheet for me. Okay, you'll see it running optimization for 31 different parameters, 31 different values. And finally here, it's told me, okay, so I have my cell G9. G9 was the number of fabrication hours. So when G9 is 1850, then we make 38 chairs, 249 tables, desks, and 100 tables for a profit of 83.61. If I had 100 more hours of fabrication available, 1950, then I would make a few more chairs, a few more desks, and still the maximum number of tables for a better profit. If I got more fabrication hours, I'd make even more chairs and desks for a better profit. But what you'll see is at some point, up to about somewhere between 2150 and 2250 hours, we actually make all the desks we can possibly make, 300. Okay. So the decisions we make bump up against another constraint, the demand constraint for desks. Okay. At which point, from that point on, we have to start making different decisions for how to optimize profit. We actually start making fewer tables and more chairs. Okay? So we can make more chairs with those fabrication hours, but we need to make less tables, okay, in order to keep the other constraints satisfied, for example, the minimum percentage chairs and so forth, to get optimal profits. Okay? But what you'll see is up to about somewhere between 29,000 or 2150 and 3050 fabrication hours, we've started making all the desks we can and all the chairs we can, in which case we're being bound by other constraints such as assembly hours and shipping hours, and we can get no better of a profit. So beyond that point, we make the same decisions for the same optimal profit. Okay. All right, I'm going to walk through that whole step again. We're going to do a different parameter, but I'm going to walk through that whole thing again and generate it so you can see it again. Okay. So let's say we don't care about fabrication hours. We'll leave that at 1850. Okay. Maybe what we're interested in maybe what we're interested in is how much profit would each chair have to make, minimum and maximum, before we'd make other decisions. So maybe this is the parameter, the profit of chairs we're interested in changing. So again, I'm going to select an empty cell right next to it, just to be easy. I'm going to click the parameters button, optimization. So I'm going to change a parameter and re-optimize. And let's say, well, maybe we'll make $0 per chair at a minimum, lower bound, and maybe a maximum of, let's say, $30 per chair. So those are my bounds, my lower and upper bounds. So again, I have my PSI opt param function. I'm going to go to the profit for each chair, and instead of saying that's always 15, I'm going to set that equal to the cell that has the PSI opt param function in it. Okay. Say OK. So now I have my profit per chair being based on a parameter that I'm curious, as it changes, what else would change. Okay. And again, I'm going to run a report. So reports, optimization, parameter analysis. Okay. Actually, before I do that, I'm going to show you one other trick, okay? And that is I'm going to select the profit cell, E7, and I'm going to give it a name. So in Excel, you can actually give cells a name. Instead of E7, maybe I should call this profit, okay? And you'll actually see here, sort of in the upper left portion of the sheet, the reference E7. When I've selected cell E7, I can actually click on that and change its name, say to profit. And I can do the same thing with my decision variables. B4, well, that's the number of chairs. C4 is the number of desks, so I'll call it desks. And D4 is the number of tables, I'll call it tables. Okay. And now when I go to run my optimization report for parameter analysis, what you'll see is, so again, the parameters in B8. I'm curious in B4, C4, D4, and E7. Okay, but you'll actually see, actually I better remove these first, sorry, because I've already done this before. I can actually add the name cells, so number of chairs, desks, tables, and profit, as the things I want to see in the report. So let's run the report. So again, it's going to run 31 optimizations. I asked for 31. And you'll see it's changing here the profit per chair one by one. Okay. And now it's computed. And here it's given me the labels of the cells as I named them. Okay. So if chairs make $0 profit, we still wanted to make some to get an optimal profit. Okay. If chairs make $1 in profit, we still choose to do the same thing, same decisions, 38 chairs, 249 desks, 100 tables. But obviously we get a little better profit because now each chair gives us $1 more profit, right? And so on and so forth, up to $15. Okay. Once we can make $16 on a chair, then it's better to make more chairs and less desks. Okay, I'm going to go back to the other sheet just for a second. So remember, we can make $24 per desk, but they take longer to fabricate, assemble. Okay, but once we can make $16 per chair, then the optimal decision becomes making more chairs, fewer desks, for a better profit. Up to, again, another point, which is $21 per chair profit, in which case we should make all the chairs we can, 360 if you'll remember, and fewer desks, and in fact fewer tables than we could. So once we can make $21 per chair, it's best to make all the chairs you possibly can, and then just however many desks and tables can be made with what hours are left for a best profit. And then you'll see that pattern should hold throughout the rest. So anything over $21 or $21 or over is sort of this break-even point where the best or optimal decision becomes making all the chairs you can, all the chairs the market will allow you to sell. Okay. There is no point, at least down to $0 per chair, there's no point at which we would decide not to make any chairs. Even if we don't make any money on them, it was still worth making chairs. Okay, oddly enough. Because again, there's another constraint that says you have to make at least 10% of your product in chairs. Okay? So even if we can't make a profit on them, we still had to make some. But we made as few as possible, subject to that constraint, and then made desks and tables to offset it for a better profit. Okay. All right, any questions about parameter sensitivity or this is optimization sensitivity. We're changing a parameter, but we're re-optimizing. Okay, so we're computing a new optimal solution for changes in a parameter. Okay. All right. Just out of curiosity, let's just say, let's get rid of the constraint on the percentage of chairs, so this E16 constraint. So I'm just going to uncheck the box in the model tab here. Okay, So we're no longer going to apply that constraint. And now let's rerun the report. Because I'm just curious to say, would we not make any chairs, right? If we didn't have to make 10% chairs, at what point of chair profit would we stop making chairs at all? Okay. So now that we're allowed to make 0 chairs, you can see somewhere between $15 and $16 of profit per chair. Okay, these two values here. Somewhere between that, we decide to make no chairs. Okay, so if we can at least make $16 per chair, then we shouldn't make any chairs, right? 0 chairs. That would be called, by the way, the break-even point. Or other text would call that the shadow price. Okay, it's the point at which you have to make this much per chair profit to make it worth making chairs. Okay, and we use optimization sensitivity to find that point, the point at which our decision changes. Well, now what's interesting is if you can make $15 per chair, then don't make any chairs, and you'll get a profit of $8,400. If you can make $16 per chair, then you should make lots of chairs, right? Fewer desks, but for the same profit. Okay, so at that point, making chairs, even though we can, got us no better of a profit, right? Now, obviously, if you can make $17 per chair versus 16, then you can make the same decision, 330 chairs, but you'll make more profit because now you're making $17 per chair instead of 16. Okay. All these are just ways you can look at this information, help you make decisions. Okay. So again, we've made a model to help us optimize a decision of how many chairs, desks, and tables to make. But there might be a point at which we say, well, how much profit would we have to make in per chair before it's worth making chairs, right? Or how many hours would we have to have in the fabrication department, right, before we could make all that the fabrication would allow us, but are constrained by a different department? That is, we should hire more people maybe to work fabrication, but at some point hiring more fabrication workers isn't useful because you don't have enough assembly workers or shipping workers or something else. Okay, so we can use optimization sensitivity to answer those kinds of questions, make those kinds of decisions. Okay, are there any questions about what we've done tonight? Linear optimization. We've talked about allocation models. We've talked about coverage models. We've talked about blending models. Okay, blends of constraints, proportions, and things like that, or weighted averages. All of these were linear, right? And even when we had a blended constraint that involved a proportion or a weighted average, we converted it to be a linear function or linear inequality so that we could use the linear optimization model to solve it. Okay, great. Well, we did not get to network models tonight. That's okay. Next week, we'll cover network optimization, which is another kind of linear optimization. Then we'll talk about how that constraint type that constrains things to be whole numbers, we call that integer optimization, and a special form of integer optimization called binary optimization. Okay, so there's still lots more linear kinds of optimizations we can do. We'll talk about those next week. And then we can talk about nonlinear optimizations. So when you have functions that aren't linear functions anymore, something with a square root or a squared function or a logarithm or something else, we can use other kinds of algorithms, other kinds of models to solve those and still find solutions. Okay, so we'll talk about all those things next time.